Hello students, in this lecture I will explain why the motor starts. DC motor draws a heavy current at the time of starting, and what we can do to reduce this starting current to a safe value. So as you know from the previous uh, lecture, we can write the armature current as V minus E upon Ra, supply voltage minus back EMF upon the armature circuit resistance. This back EMF or induced armature EMF is proportional to speed if the flux is constant. So it is V minus K omega M upon Ra. At full load, a shunt motor or separately excited DC motor is designed such that the back EMF is about 95% of the supply voltage at full load. So at full load, the current will be equal to 0.05 V upon Ra. If suppose the supply voltage is 100 volt, resistance is 1 ohm, then full load current the motor will draw will be equal to 5 amperes. What happens at starting? When you start the motor, the switch on the supply. Then what happens? The motor is stationary, speed is 0. So what is the current there? V upon Ra. So if I put the value of V here, it is 100 upon Ra. So it is equal to, it will be equal to 100 amperes. So this current will come out to be equal to 100 amperes. And this is, you can say from here, that it is 520 times the full load current. The motor which was designed for 5 ampere current will draw a current of 100 amperes at the time of starting. So the starting current in DC motor is very high, maybe 20 times, 30 times, even 50 times of the rated current. So this depends on the value of the resistance and the design of the motor. So this current is very high, and this current cannot be allowed to flow even for a short interval of time. What is the permissible value of the starting current? Normally, for normal motors, the current could not be more than twice the full load current, and for specially designed motors where we use commutating poles, this current may be 3.5 times the full load current. Because what happens is that if the current is very high, then one thing is that it will cause overheating of the armature winding, but the major problem comes in commutation. The current will not be safely commutated, and it will cause sparking at the brushes. So that will reduce the life of brushes and the commutator segments. So starting current should not be more than twice the full load current in a normal designed motor, and for a specially designed motor it can be up to 3.5 times the full load current. So this has to be limited. Main problem is this, because of commutation failure. In the case of induction motor, the current drawn is normally 5 times the full load current at the time of starting. So in that case we can start the motor without a starter, because the motor will start up very quickly and reach the rated speed, and the motor will not be overheated because of current drawn for short interval of time, because heating takes place on time. As you remember, in the previous unit we discussed the thermal time constant of the motor. It is quite high, so the temperature rise will take say 20 minutes, 30 minutes or 40 minutes. So the flow of current for short duration of time will not cause much heating in the winding. So that is not the problem. So induction motor can be safely started without any starter. But in the case of DC motor, it is a must. You have to use a starter when you want to start a DC motor. So as you see here, this starting current is equal to V upon Ra. So what is the remedy? What you can do to reduce the starting current? There are two possibilities. Either you reduce V, the supply voltage, at the time of starting, or you increase the armature circuit resistance at the time of starting. That is, you insert some external resistance in series with the armature at the time of starting, and as the motor speeds up, this resistance can be gradually removed from the circuit. So these are the two methods which can be used for reducing the starting current. If the motor is used for only for full load speed, for the rated speed, speed control is not required, then we shall not be using any voltage control technique to reduce the voltage. So in that case, we have to go for this second method, that is we have to use some 3-point starter or 4-point starter, which inserts some resistance in the armature circuit at the time of starting, and as the motor gains speed, that resistance is gradually cut out from the circuit. But if the motor is used for speed control purpose and we have some arrangement for voltage control, then we need not to go for this starter, and simply you can reduce the voltage at the time of starting, and gradually you can increase the voltage as the motor gains speed. So let us see what happens, what are the dynamics during this starting process. So let us take the first case where we reduce the voltage at the time of starting. So I have drawn here the characteristics of the DC motor for different voltages. You can, if you recall the previous lecture, the speed is given by V upon K minus RA upon K times IA. So this is the y-intercept, this is no load speed. So if we vary voltage keeping RA constant, RA upon K is the slope of the characteristics, so this remains constant, only the no load speed will change. So as we reduce the voltage gradually, for 1 voltage this is the normal characteristics, for rated voltage, for reduced voltage this is the characteristic, for further reduced voltage this is the characteristic. So characteristic shifts downward parallel to itself as the voltage is reduced. So what you have to do is that at starting we have to keep the voltage such that current is limited to the safe current, that is maximum permissible current. I have taken it to be twice the full load current. So we have to reduce the voltage to such an extent that when we start the motor, the current drawn is equal to twice IAFL. So this is starting point. So because of this current, the motor develops a small torque. Motor will speed up, speed will increase, and the operating point will shift here. When it reaches the full load current, then you can further increase the voltage such that current again becomes equal to twice the full load current. Then again, because of this increased voltage, again the motor will speed up as the torque is produced, and the operating point will shift from here to here. Again we increase the voltage, and in that way, gradually increasing the voltage, we can reach the final rated voltage, and the final operating point will be somewhere here. So this is your final operating point when you have increased the voltage gradually. So care has to be taken that you have to increase the voltage only gradually, otherwise the current may exceed the safe limit. For example, instead of reducing the voltage, let me number these voltages. So suppose this is the 1, 2, 3, 4, 5, 6. There are 6 steps of voltages, and finally we reach the rated voltage. So instead of increasing the voltage from level 1 to level 3, then what will happen? Or level 4. In that case, if we increase the voltage from V1 to V4 directly, then what will happen? That for V4 this is the characteristics. So starting current, the current will exceed and it will reach here. So it is much more than the permissible current. So you have to take care that the voltage is increased only gradually. So this is the case. And in case we directly apply the rated voltage, then what will be the current? You can just go on extending this curve. It will finally meet this x-axis at some point. That will be the starting current of the motor. That is maybe around 20 times the full load current of the motor. So this is first way we can reduce the starting current. Second way is increasing the armature circuit resistance. That is, we insert some resistance at the time of starting. So what happens is that This is the normal characteristics where we have not added any external resistance. And if keeping the voltage constant, we increase the resistance of the armature circuit, then what happens? The slope of the characteristic will increase. The starting point, that is the no load speed, will remain same. So the slope will increase. So we have to insert such a resistance that when you start the motor, switch on the supply, then the current should be equal to the maximum permissible current. So add such a resistance which causes this condition. So add a resistance, motor will start here in initial operating point, and the current will flow. As the current flows, the torque is produced, motor will accelerate, operating point will shift here, and as we reach the full load current or below that, we can reduce the external resistance such that this becomes the new characteristics. So this is zero resistance, say 1 and 2. I have for clarity I have taken only 2 steps. So here you have decreased the resistance to R1, operating point will move here, and again it will accelerate, and here again we have reduced the resistance and removed the external resistance. So as soon as we reduce the resistance or remove the resistance, speed doesn't change instantaneously because the motor has a high mechanical time constant. It takes some minutes to change the speed. So this means that as soon as we reduce the resistance, the operating point will shift immediately to this point. And now because of the torque, the motor will accelerate, and finally we reach the final operating point like this. So in that way you can keep the current of the motor within safe limit, and motor will start up quickly and reach the final operating point. So these are the two methods which are used for starting a DC motor. That's all for today. Thank you.